In the previous lessons, we learned about the definition of acid and base and how an acid and base in a chemical reaction will have a conjugate pair. And we used the definition in terms of the Bronsted-Lowry. Basically, a Bronsted-Lowry acid will donate an H+. This is also known as a proton. On the other hand, the Bronsted-Lowry base will of course accept the H+. So keep that in mind. Acid is about the hydronium ions. Well, in this case, we have the Arrhenius acid. Well, Arrhenius acid ionized in water. Well, the term Arrhenius acid or base is relative to how the substance interact or ionize in water. Well, for Arrhenius acid, it will ionize in water and produce the H+, just like the Bronsted-Lowry, where the Arrhenius base will ionize in water. That means it will react with water into ions. The term ionize, basically, you have a substance like right here, HCl. Well, we know that hydrochloric acid or HCl is made from a positive H+ and Cl-. Well, when it's being ionized in water, it will produce H+ ions, hence the term ions, and Cl-. The same thing for the base. Here we have NaOH. This is from the plus Na or sodium and the OH- hydroxide. When it's ionized in water, notice the term ions, right? It will produce the positive ions and the negative ions. Well, in this process, the base produces the OH-, which is the hydroxide, where the acid produces the H+. So keep that in mind. That is extremely important when it comes to calculate pH. Before we look at the calculation of pH, we need to look at that there are different in terms of strength of different acid and base. Well, first of all, a strong acid and bases will completely ionize or dissociate in water. What does that mean? All the substance in water that is a strong acid or base, it will break into ions, no longer stay as NaOH or H+, okay? So they will be ionized in terms of becoming ions in that water solution. Basically, the strong acid and base will all become ions. Now, if we mix a strong acid or a strong base, okay, when we mix them together, what happens is that both of them will become ions, and those ions will form a salt, okay? And this salt is extremely strong, usually is bound by an ionic bond, and it's also produced water molecule as well. So basically, when you have strong acid and base, they will react with each other and form a salt and water. And most importantly, that this reaction has no reverse reaction. That means the salt will never be broken back and form the acid and the base again. This is just a forward reaction. There is no reverse reaction. Now let's talk about the weak acid and base. Well, strong acid and base completely ionize in water. Of course, the weak acid and bases will be partially ionized in water and with each other. Here are two common ones. This is the acetic acid right here, and this is ammonia. Well, we have two things. Notice how we have Ka and Kb. Remember, this is equilibrium constant. We also can express it in terms of acid and base. And when we have Ka, is talking about the equilibrium constant of the acid. Notice how we have A, dissociation constant. That means how much of the acid will be dissociated, that means break into ions. And then we have the Kb. What do you think B represents? Of course, for the base. So this Kb represents the dissociation constant of a base. How much of that base will be dissociated or ionized into ions? And of course, if we look in terms of Ka, the larger the Ka, of course, is going to be the stronger the acid. Because the stronger it is, it will be ionized into ions. And the same thing for Kb. The larger the Kb, it will be ionized into ions. And of course, it's going to be the stronger the base. And that's how we determine the relative strength of strong acid and base versus weak acid and base. Now let's learn how to memorize the strong acid and base? Well, for the strong acid, it's basically the hydrogen plus the halogens. And the other three major ones, HNO3, which is nitric, and H2SO4, which is supposed to be like this, H2SO4, sulfuric acid right there, and HClO4. Those are the major three that you have to remember individually. And the rest is just hydrogen plus the halogen. What do I mean by that? So you look at the periodic table, right? We know the first halogen is F, the second one is Cl, Br, and I. And all you do is adding an H in front of it. And all those are strong acids right there. Isn't it easy? And for the strong base, it's just group 2 plus the hydroxide. And remember, hydroxide is OH minus, right? And group 2, what's in group 2? Like, for instance, calcium, OH minus. And of course, there you go. Barium hydroxide, OH minus. All those are strong base. So that's why we have the hydroxide right there. And for the weak acid and base, there's a bunch of them. So just remember the strong one. If they're not strong, therefore they are weak. Now, we also have a new term called KW. Basically, KW is, well, think about it. What does W represent? Of course, it's going to represent water. So KW represents the dissociation of water. How does water become ions? Remember, water can be a base and an acid, so it can actually ionize itself into ions. So keep that in mind, and we'll talk more about this later. Now let's get back to the pH scale. Well, first of all, the pH scale, we learned this already. It indicates how acidic or basic a substance, more specifically in terms of the concentration of H+, okay? So the more H+ you have, guess what happened? The more acidic you're going to become right there, right? Because the Arrhenius acid produce H+. So the pH scale talks about the concentration of H+. Well, the pH scale depends on two independent, that's very important. They are independent factors. The first one is the degree of ionization based on its strength. The stronger acid is ionized completely. But here's another factor. It is the concentration of the solution. You can have a strong acid and you put that acid in a lot of water. That solution is not going to be anything dangerous. But if you have a weak acid, right, and you put in a small amount of water, that weak acid is still corrosive, or even more corrosive than you have a strong acid in a large container of water. See the difference? So depend on two independent factors, the strength or the degree of ionization and the concentration of the solution. Now pH is not the only letter that deal with P. Okay, we'll talk about that later. We also have pOH that talk about the concentration of course, OH minus, right? Then we also have pKa, pKb, and pKw. And notice, what do they all have in common? Of course, the letter P. And here is the most challenging part of all, is that letter P right there. What does that letter P represent? Well, that letter P, mathematically, is actually representing a negative log to the base of 10. So this is extremely important. So if we have a negative log, well, in this case, if you have P of anything, it's equal to the negative log with a base of 10 to anything. So if you have pH, okay, let me rewrite them over here. So we have pH. Of course, this is going to be a negative log of base of 10 to the H+. Okay? And that's extremely important. Why is that? Because now, if you are given pH, you can actually solve for the concentration of H+. Or if you're given the concentration of H+ or OH minus, Ka, Kb, and Kp, you can solve for any of the pKa, pKb, or pKw. So how does that work? So once we have this, if we're given the concentration, that's pretty easy, just solving pH, right? That's plug in. But what if we're doing the other way around, where we have to solve for the concentration? Well, that gets tricky over time. Let me show you how that's going to work. Well, first of all, you need to move the negative over here, isn't it? So you have negative pH equal to log of H plus. And of course the base is 10. And here are the two most important common rules about log. And it's extremely important. Well, the first thing is that if you have log with a base of 10, and this log base of 10 is to 10, that cancels out equal to 1. Why is that important? Because anything multiplied by 1 is equal to self. Well, in this case, if we look at this, right, what if I put 10 to the power on both sides? Well, what do we have here? We also have another pattern. That is, this is called anti-log. Okay? So basically 10 to the log with a base of 10, what does that happen to the number of all this madness right here? It turned out as simplified equal to 1 as well. So this whole entire thing right there, it's actually equal to 1. So now we have 1 times the concentration of H plus equal to 10 to the power of negative pH. And if that's the case, of course we can now solve for the concentration of H plus or OH minus. You see the power of anti-log, and these two important rules right here. Now let's talk about this part right here. How can we use this to estimate our pH? Because pH is about negative log of something, right, with a base of 10. So in this case, let's look at this problem. Estimate the pH and pOH for each of the following solution at 25 degrees Celsius. Well, if you look at this, we have to make our problem in a way that's 10 to the power of something, right there, okay? Now notice why it is 1. Notice why this is equal to 1. Because if we were to write this like this, we have log to the power of 10. That 10 is actually equal times 10 to the power of 1. And that's the beauty behind it. That 1 right there is actually equal to that. So this part cancels equal to 1. And 1 times 1 is what? It's equal to 1. So in this case, we can use this mathematical relationship to estimate the pH. Well, we are not given in terms of scientific notation, right? But we can actually convert this into scientific notation in some way. Well, here we have this one right here. I just moved the decimal 1, 2, 3. So we would have 3.5 times 10 to the, of course, negative 3. Now, why is that important? Because now we have that 10 right there. Because if I were to put a log of base of 10 to 3.5 times 10 to the negative 3, I can't just ignore this part, right? Because we are estimating. So if we were estimating, what do you think we're going to get? Well, of course, this will happen to be cancel out equal to 1. And that would be about 3. Remember, pH is equal to negative log. And that's why this becomes a positive. If there's no negative here, it would be a negative 3. But pH is equal to negative log. So our estimation is 3. Let's prove that, okay? So we have pH, which is negative log of 3.5 times 10 to the power of negative 3, give us about, well, exactly 2.5. So that is very close, isn't it? And that's how we use the concept of the log rule to estimate our pH. And notice how this is sulfuric acid is extremely strong acid. Well, in this case we have a weak acid, but it's the same concentration. So this is going to be acidic, isn't it? Based on the pH scale. The closer to the 0, the more acidic it is. 7 is neutral, 14 is basic. Now let's get to this part. Of course, it's going to be the same scientific notation number. We have 3.5, okay, times 10 to the negative 3. Well, if I take a pH of that, which is going to be what? Notice how this is an acid, that's why I take the pH, because we are giving the concentration. That's why it's important to know that the Arrhenius acid produce H+. Well, in this case, both of them are acid. It will produce the H+. If it's a base, it would not produce H+, and we'll talk about that later. Well, in this case, negative log of this, of course, to the base of 10, we can make the same assumption, that's about 3. And if I were to plug this in again, of course it's going to give me the same number, negative log of 3.5 times 10 to the power of negative 3, give me 2.5. Which, look at that, it's the same, isn't it? So that's why it's important to understand that pH is based on 2 independent factors, the strength and the concentration of solution. Okay, so keep that in mind. Now look at this, we have a base which is going to produce the OH minus. So can we do a negative pH? So can we use pH to determine the concentration of OH? Of course no. We have to use pOH, okay? And of course P is equal to negative log. In this case it's going to be negative log of what? Well, remember this is a base of 10, and that is going to be the negative log of the concentration of this base, which is 4.2 times 10 to the negative 4. And of course this can be ignored, and we focus on this 10 and that 10 cancel out equal to 1, and the negative and negative, well, of course it's going to be a 4. So this is our estimation. Let's prove that that's going to be a good estimation or not. Well, of course, negative log, okay? Negative log of 4.2 times 10 to the negative 4 give us, look at that, it's equal to 3.3, well, let's call it 3.4, how about that? And this is equal to pOH, okay? Keep that in mind. Now, how is pOH related to pH? Well, you learn in regular chem that pH plus pOH is equal to 14, and that is the entirety of the scale, right? You add together equal to 14. So in this case, we can actually solve it by looking at this, pOH equal to 14. Now I know what pOH is, which give myself pH plus 3.4 equal to 14, and of course pH is equal to what? 14 minus 3.4, and that will give us our pH. So let's prove it. Let's just plug in the calculator, minus 3.4, and give us 10.6 in terms of pH. And look at the scale, isn't it right? Look at it, this is 10, somewhere right here, so it's gonna be basic. If we were to using pH to solve for pOH, it wouldn't work because 3.4 would be acidic, right? So this part is extremely important. Make sure you understand or know how to identify the base in an acid before you can apply the negative log of something. Well, let's estimate the pOH. Now let's estimate the pH using our estimation. Of course, again, the same thing, pH plus pOH equal to 14, and that right there is a 4. So pH is equal to 14 minus 4 give you 10. So that is a pretty good estimation right there, isn't it? Give us a good idea that this both are about the same. And this skill can be applicable in a multiple choice problem.